Do that? So we're going to look now today at the imaginary number system for the first time. We've talked about this. We've alluded to it. Okay, it's like a big, lead up to whatever this really is. But most of you have an idea already what it is. We've alluded to what brings about an imaginary number. Does anybody remember what brings about an imaginary number?
5 by 0.
That's an undefined number. Okay, and that's not. It's different. Okay.
The radical of a negative number.
The square root of a negative number. Okay, the square root of a negative number is what causes something to be imaginary. So what we're going to look at today is we're going to look about first, where did it come from? And then second, what are some tricks or some patterns to pick up on? So consider the equation where you have x squared equals some negative number. Doesn't matter what it is. In this case, negative 1 we'll look at. If you have a negative number, we have to think back. Is there any possible way that the same number multiplied by itself could give you negative 1? Could that ever happen, honestly? It can't. It's impossible for any real number, again, I should say, any real number to be multiplied by itself. You can never get a negative, because when you square a number, you always get a positive. So the question is, what kind of a number could you square so that you'll get a negative? Well, we came up with this other number system. And this other number system, believe it or not, is probably more important than a real number system, which you would never think about, because every day in life, don't you really refer to real numbers? Do you ever talk about something where it's an imaginary number? No. To this point you definitely haven't, and you probably won't. But if you look at science, technology, if you look at anything that has to do with systems that are moving, things that are periodic, anything that is like a satellite, your cell phone, all this stuff, nothing you could ever imagine electronically would work without the imaginary number system. Electronics, especially if you're looking at feedback loop systems. So for example, if you're on an airplane, okay, and ever wonder an airplane why it doesn't shake a lot? Because there's definitely wind. You're up way above, you're going like 400 miles an hour. How come the plane's not shaking the whole time? Why is there only turbulence sometimes? What's physically happening? Anybody know? Anyone study airplanes ever? Or anybody watch a documentary on airplanes ever? How do they work? How do they take into account some adjustments while they're flying? Say the wind comes in on the right side, right? And it causes the plane to do this. How does it adjust to rebalance the plane? There's definitely gyroscopes involved. Gyroscopes measure balance to see if something is directly straight up or turned. Anybody know specifically on the plane what part adjusts itself in order to change the pitch or the yaw?
The wing.
What?
The wing.
Yeah, it's on the wing for sure. On the wing, ever look out the wing? What do you see? Yeah, did you ever wonder what that was doing or not? Did you know that that's what it was? They're called flaps. The flaps, yeah. So when you're landing, you ever see the flaps go out? If you're on the wing, look out next time when you're landing. You'll see the flaps all like this when you're landing. Why do they do that?
They go up.
Why do they go like this?
Is it like you're pushed against the wind resistance so you can measure?
Exactly. So here's the wings, right? Here's my wings like this. The flaps are like this little piece on the end of the wing. The flaps angle this way when you're slowing down, as well said, to act as resistance against the wind. When you're lifting off, though, the pitch is different on it, right? So you're going to see the angle change, and that angle is constantly changing as a function of what the plane feels. So once the pilot gets you off the ground, this is not a joke. Obviously I don't take anything away from pilots. They're very intelligent, and you need them to get places, right? But once you take off, after that, what's going on? Anybody know? What do they press?
It's kind of like an automatic.
Yeah, it's a cruise control. It's not any more than taking off and then landing. Unless you get to you imagine you're flying through a storm and there's turbulence, sometimes they have to take manual control to, stabilize the plane a little bit more. But the system on the plane is such a stable system that it automatically knows that anything goes wrong, it knows what to do. And there are fault-proof systems in there. So if something breaks or malfunctions, maybe a light turns on so the pilot knows what to do himself, or there's a backup system in place. So in order for the plane to actually understand what's going on, it needs to have a control. So it knows what the angle of the plane should be. It knows its current altitude. It knows its velocity. If suddenly the plane's speed slowed down because winds, it would adjust. It would cause more thrust to come out of the motors, speeding it up a little bit. And sometimes it can't overcome the winds, and you get delayed flights and different things and storms. Now, for those feedback things, those little, and when I say feedback, what I mean is this. The system has this little control in it, all right? And something goes into the control, some signal, and comes out of the box and it tells it to do something. So say here it's it would never say this in words, but if the wind on the left side of the plane, so say there's wind on the left side of the plane, suddenly it feels wind. what it does is in like an infinitesimally small amount of time, like a microsecond, it decides adjust the flap. And that's the outcome. And I don't even know, to be honest, which flap it would adjust and what angle, depends on the situation. But it goes into the system, it says, something's going on, what do we do with the response? Quickly do it. But this happens so quickly because it's a computer that it's called a feedback system. It's constantly monitoring. Any change, it automatically feeds back. All of the math involved in this involves imaginary numbers. All of the math involved. A lot of engineering involves imaginary numbers. Almost every type, maybe not civil. It's probably the only one I've seen. Actually, no. They have them too. If you're looking at matrices, they have imaginary numbers involved. But for electrical, computer engineering, mechanical engineering, a good amount, civil not as much, maybe some chemical. But imaginary numbers are so apparent every day. As everyday people, you don't see them, right? It's not something that you're like noticing or understanding even what's happening. But if you're looking at like the train system, the mechanics, the electricity, and the system that goes into that, there's imaginary numbers used in those calculations. Okay, so it's really important to understand that although this is a topic that's not really taught until now, and you're not going to see a ton of imaginary numbers in pre-calc and calc, you'll see it for sure, but you won't see a lot of it. If you go into a science, math field, you're going to see this. Probably more often than you're going to see the real number system. Okay? So let's continue. In order to solve this equation, this x squared equals -1, we invented this thing called I. All right, we invented this thing called I. So, and I'm going to put an example down here to make it a little bit simpler. So if we have the square root of -4, for example. Well, what's the square root of 4? Just 2, right? Let's say the principal square root for now. Yeah, just 2. Now, clearly this is not just 4, but I could say this, right? Can I just break this up? Can I break this into this? Isn't that true? Does that make sense so far? Logically it makes sense? So, since the square root of 4 is just 2, that part's easy. This becomes a 2 over here. But what about that square root of -1? Well, that's the problem we're having now. Okay, we don't know what that is. So what we say is we give it a definition. We call it I. I is defined, look at the top. I is defined as the square root of -1. That's the definition of the constant I. It's just some made-up thing that allows us to perform calculations with imaginary numbers involved. Okay? So imagine that every time, consider that every time you have an imaginary number, it comes from the fact you have a negative under the square root and you really just factored out a -1. So this becomes I, and the way you write this is, usually you write it as 2I. The number first and then the imaginary part afterward. So again, the definition of I is the square root of -1. So see, I put or, because if you think about this, right? Look at the statement at the top. If you square both sides of this that's circled there, you get this. Right? Square I, you get I squared. Square the square root of -1, you get -1. All right, so the next line, that's what I was saying with this idea right here with this example. It's a little easier. Take out a -1, reduce whatever this is, make the -1I under the square root, that comes there. That's what this is saying right here. So if you have the square root of a negative value, make a -1 times the positive value. The square root of -1 is I, and then whatever this becomes goes there. Now again, if this comes out to be a number that's an integer, usually it goes in front of the I, not after the I, as you see there with the irrational. Is that what you're going to ask? Yeah. When an answer cannot be simplified, for example this, you don't write it with the number in front, you write it after. And this is just, it's kind of stupid the reason that this is done. All right, so this becomes I root 5. Traditionally, you put a radical at the end of an expression. That's the reason that happens. Okay? That's why this goes here. But when you have integers, they always go in front of them. You're just going to see that over and over again. All right, so let's take a look at some. So example A, everybody should be able to do this. Quick as anything. Break up into -1 and 36, which is just 6I. Okay, part A is definitely 6I. How about part B? What would you break up 32 into? What would you break it up into? I agree. Okay, does that make sense? You still break it up as if you would break it up earlier in the year when you simplify radicals by looking for the largest perfect square that goes into that radical, or into that radicand, rather. Okay, so 16 and 2. So we have I we have a 4, and we have a root 2, which can be written as 4I root 2. Again, the integer first, the imaginary part next. The radical always goes on the end of the expression. Is this easy enough? Does it make sense? It's something that you haven't learned before, but it's not a difficult thing at all. It's just an idea of a new number set. Completely new. So if you recall, by the way, you should actually think about this. We had talked about real and imaginary numbers when we broke up. Remember in the beginning of the year, we went like this. We took the overall number systems. We said some are imaginary, some are real, and then there's rational over here, and then there was irrational, and then within rational there was whole numbers, integers, accounting numbers, okay? The imaginary number system is completely separate from the real number system, but it has real numbers in it. So this example here, this is called an imaginary or complex number. That's what this is really called here. Well, it's got real parts to it, and it's got imaginary parts to it. So it's combined of both, really, although it's in its own system. Okay, and some people will say, call this complex. And then that is broken up further into like pure imaginary. And I think mixed, but it doesn't really matter. The idea being this. The idea being you could have an imaginary number such as, ready? 2 plus 3i. Where it's mixed between a real part and an imaginary part with two different terms in it. Okay, and this is actually one of the most important things you're going to see. With, you call this A, you call this B. And based on the values of A and B, remember what I was talking about earlier with the cruise control on the plane? Based on those quantities, these numbers, you can determine if its system is stable versus unstable, whether it should change or not. So you're looking at the signs of those values actually in the end. All right. How about we simplify these two? Try A on your own. A should be pretty easy. And B should be pretty easy as well. But think about A as if I were a variable when you're adding together. When you're adding together, think about I, when you take it out, as a variable term. We got it. Yep. Very good. Check your answer, please. Part A was really simple. You should have gotten 8i minus 10i, and 8 minus 10 is negative 2, so it's negative 2i. Again, when you're adding and subtracting, think of I as a variable. Part B, when I split these up, clearly I'm going to take the I out from both of these first. 8 is 4 and 2, 18 is 9 and 2, 4 is 3, 4 is 2, 9 is 3. How do I add these two together at the end now? It looks more complicated than it is. Think about the same rules we know.
Just add 2 and 3, you get 5i, radical 2.
Very good, Ben. Square root 2, radical 2. Same thing. Okay, 5i, radical 2. Again, add the coefficients, just like radical 2 were a variable. Remember? You have to imagine that this is a variable here and here, and think about this as a coefficient and this is a coefficient when you're adding those together. I'm reminding you over and over again, because when you learn this during class, it's not hard, right? But when you have to remember everything, and then you're taking a test where all these rules are at the same time, you need to distinguish and differentiate between which rule you're going to use. So you should understand for something like this, to think of that radical as if it's a variable, it makes it easier on you. All right, what about multiplication? It's going to get a little trickier now. Any suggestions for part A? Any suggestions for part A? Yeah.
For the square root of negative 9, you get 3i. And then for the square root of negative 16, you get 4i. And then you would multiply it to get 12i squared.
Okay. One more step. Anybody see it?
So it's square root or
No. No square root. I should put an arrow here, not an equals. No equation involved.
It's negative 12.
Why is it negative 12?
I squared is supposed to be negative 1.
Remember I squared was defined in the beginning as negative 1 actually? Go back to the second slide or whatever it was. We defined I as the square root of negative 1. So by default, I squared is really negative 1. So it's negative 12. Very good, Luca. Way to pick up on that. Good work through there, Kelly, with the problem. How about part B? How about part B? What can I do there? What do you got for 32? They're both going to take i's out, obviously. So we can, we could always start doing this right off the bat. What do you got, Mike, for 32? What does 32 break into?
16.
16 and 2, good. And the next one? 12? 4 and 2. No, you had it. Because remember, you want a perfect square. 6 is not a perfect square there. So we've got 4i root 2 times 2i root 3. What should I do next?
Multiply.
Okay, giving me
8i squared root 6.
8i squared root 6.
So negative 8 root 6.
There it is. Okay, remembering as Charles did that when you multiply two things with radicals, you multiply the outsides and you multiply the insides. Okay, the 2 times 3 gives you the 6 under the radical, and the 4i times the 2i gives you the 8i squared. There's a few more examples I want to go through real quick. I want to prove something to you real quick. Look at example A. See example A. If initially we hadn't taken out the I and we multiplied, this would not hold true. What's negative 9 times negative 16? Imagine you just multiply to start, because you can do that technically. With real numbers you can do that. Let's see what happens with imaginary. What's 9 times 16?
144.
144. So we have negative 9 times negative 16 is 144. And what's the square root of 144?
12.
12. But we got an answer of negative 12 earlier. So this rule of multiplying only works when the radicands are positive. Again, you want the root A times root B equaling root AB. This is like the rule you can multiply underneath. Does not hold true if both A and B are negative. Okay, this only works for A and B as positive numbers. All right, that's what I'm trying to say. Negative or root negative 100 times root negative 25 does not equal root 2500. You cannot multiply two negatives to make it a positive under the radicand. You need to instead take I out first. All right, instead of that, take I out first.
So if you get an imaginary number in the denominator, do you have to get it out?
So you simplify it first. If it still has a radical, say you had like I root 2, you have to multiply to get rid of it. And we'll talk about how to do that tomorrow when we get to that. You can probably guess is what you're going to do already. Think about, remember what we did with like the complex conjugate or the binomial conjugate, where you multiply by like root 2 over root 2. Same idea, but it can be a little bit different. You can practice if you want. Try. All right, let's take a look at these two here. So if we want to use the same technique as rationalizing the denominator, which Charles was just mentioning, I didn't even know it was the next one, Charles, nice. If we want to get rid of that 3 over 5i, think about how we got rid of a denominator that was irrational. Now the denominator is imaginary. We want the denominator to be positive, or to be real, I guess, in this case. What would we do?
Multiply by 5i over 5i.
We could do 5i over 5i. That definitely works. But I over I is probably easier because the 5 can stay there. It doesn't matter if the 5 is there. So take the first one and multiply it by I over I. That will give me 3i over 5i squared. And I squared is negative 1. Good, so we have negative 5. Okay, so believe it or not, this is actually the proper way of writing that answer, which seems ridiculous. Well, actually, you'd write it like this, really. The coefficient in front. Traditionally in math, you write I by itself, either by itself or with a coefficient, but you don't usually put I over something like you saw above there. Okay, this is not wrong up here, but this is actually better, if you will. Okay? How about the second part, part B? What did you do for part B? Think about rationalization, but also think about imaginary numbers. Put the two things together. How would you get rid of a radical in the denominator? Will, how would you get rid of a radical 3 if you just had a radical 3 in the denominator?
You would multiply by negative radical 3.
Well, only if it's like 2 plus root 3, then you do 2 minus root 3. But if it's just root 3, you could just use the positive. So tell me what to do here, Bill. So
You multiply by negative root 3.
So multiply this by?
Negative root 3.
Again, I would just use positive. There's no need for the negative because, remember, if you multiply by root 3 over root 3, doesn't the root 3 just become root 9 now? So it's okay, it simplifies. You don't need the negative. I mean, it's not wrong actually, but I probably would just leave it like that. But, Will, I also want to get rid of that I in the bottom. How do we get rid of the I in the bottom in part A?
You multiply by I.
So let's put I in front of both of those. Now, the numerator becomes 4I root 3. The denominator becomes I squared times 3. I squared is negative 1 again. So this is going to become 4I root 3 over negative 3. Now, this is a little bit weird, the way to write this one. You would usually still write it with the radical at the end and with a coefficient in front. So if I wanted to do that, what should it look like? The coefficient in front and a radical at the end. What's the coefficient in this one? I have 4I radical 3 over negative 3. What's the coefficient in this, Brown?
4I.
Not 4I.
Just 4.
No? What do you got?
Negative 4 thirds.
Negative 4 thirds. It's the integer part here that we're looking for, okay? Then the I goes, and then a root 3. Okay, but that last one, don't worry too much about writing it this way. Usually, again, though, you'll see it written where there's a coefficient and then I. If there's a radical, it's still coefficient and then I, and then the radical goes at the end still. Okay, or you could have written it, again, like this. Once you have both of them involved, it really doesn't matter. You could have written it this way also. All right, that works as well. Same thing, really. Okay, when we get to complex numbers with two parts, which you're going to see in the next lesson, we have to focus on writing it a certain way for a reason. How about example 5 now? So those first few examples are pretty easy because we had numbers. But now we have some variables involved. Now we've got some variables involved. What should we do? What should we do? Yeah. Same thing. Treat them just like we treated them earlier. Okay? So root 4 with a negative in front of it makes that 2i for sure. 2i. Then what's the square root of x squared?
X.
It's x, okay? Now we've been using absolute value of x, so to be consistent with it, well, I'm going to keep it there. All right, I'm going to leave it that way because we have that variable part there. Then I get negative 9, which will give me 3i absolute value x. So we've got 2i absolute value x plus 3i absolute value x, which gives me? Louder? 5i absolute value x. Okay, just summing these together like we would normally. And then what about part B? What about part B? Luca?
So first you take the I out and then a multiply them.
Good. That's the key here. Luca recognized that you can't do anything until you multiply them, right? So he's like, we got to multiply these things. We can't multiply them with a negative underneath. That rule we said earlier. So take the I out first, then multiply. I times I is I squared in front. 6y times 3y is 18y squared. Now it makes it nicer, doesn't it? Because now the y squared reduces to y. What do you got for the 18?
18 is 9 so it's 3i x and value y.
Good. Okay, so we're going to get a negative 1 here. We're going to get a 3 here. Absolute value y. And a root 2. I'm switching the places of these two right here. So it's in the right order. So giving me negative 3, absolute value y, root 2. Okay, again, not difficult, but you're putting together all the stuff that we've done, all those rules that you learned. So there's a lot of room for error. Okay, that's all. Let's do the last one. Okay, the last one together. So for number 6, we have this equation. Let's go ahead and take a look and solve this equation. Now that we know what imaginary numbers are, we can easily solve this. You should be able to get to the step where you have x alone by yourself now. Now I'm solving an equation, so don't forget this, please. You're solving an equation, so the answer, it should have 2 roots here, so it's a plus or minus there. I want to mention something. You can all get to that work on your own. That's not the hard part. What I mention is this. Remember in graphs so far, we've talked about these answers being the x-intercepts usually on the graph. And I mentioned that you can find either the root or the x-intercept. These are not going to appear on a graph because they're imaginary. So what you'll have is this. Take a look at that parabola at the top. That's really what it is. It's quadratic. It's a parabola. That parabola is either sitting above the x-axis, so make believe this is the xy axis, okay? That parabola is either up here or is down here. It will never cross the x-axis because these roots are imaginary. So if you want to, you could actually graph that. You could graph 3x squared, if you move the 35 over by adding it, 3x squared plus 60. If you graph 3x squared plus 60 in your calculator in y1, you're going to see a graph that's floating above the axis or below the axis, one or the other. Okay, it's never going to touch that now because these are imaginary roots. So imaginary roots, you don't see them on a real axis. If you want to plot things that are imaginary, you use an imaginary axis, an imaginary plane. It's a little bit different than the xy coordinate. We're not going to be plotting with imaginary roots, so you don't have to worry about it, but the idea is that it's different. Okay, you're not going to see those appear as roots. Again, this would look like this for sure because it's opening up. So this would be, and this is symmetric, so it's this. Okay? And this intercept here is 60. That's a y value of 60. Because I move the 35 over, it makes it 3x squared plus 60. So the y-intercept is 60. But that's what that graph would look like. There would be no x-intercepts.